Oh, hi there. I hope everything is going well with you guys. So, today, what we're going to be doing is continuing our talks about gases. So, in particular, we're going to be looking at pressure. This is on page 14 of the Gases and the Atmosphere book, Unit 3. So, what we're going to be doing today is first having a look at what pressure is and defining pressure. So the first thing we need to be aware of is that pressure is the force per unit area. So it's the force per unit area. So what that pretty much means is that pressure is the force being exerted by an object over a particular area. So if you want to take that definition and turn it into sort of a mathematical equation, we would say that pressure equals force divided by area. Some people like to think about definitions in terms of formulas, and I like to do that as well, especially for something like physics or chemistry. So in order to calculate what the pressure is, like I said, you divide the force that's being applied, and then you divide it by the area over which that force is being applied. So the first thing I'd like to do is think of some examples here. So if we consider some everyday objects, so for example, if we consider a nail, which sort of has a fine point, versus a screw that has a broader base. If we consider both of these objects and then we consider applying a force to each of them, so let's just say we're applying a force of 10 newtons to both of these objects. Hopefully you remember that newtons is the SI unit for force. Let's just say the surface area of the point of this nail is 0.001 meters squared, and that the surface area of the point of this screw is 0.005 meters squared. So if we wanted to calculate the pressure that each of these objects is exerting on a piece of wood, for example, we would use our formula of pressure equals force divided by area. So for this nail, the pressure would be 10 newtons divided by the surface area of the point, which is 0.001 meters squared. And for the nail, or screw I should say, it would be the same force, 10 newtons, being applied over 0.005 meters squared. Okay. And then what we would do to find the values of those two things is punch them into our calculator. And once we do that, we would get the pressure is 10,000 newtons per square meter for the nail, and then the pressure would be 2,000 newtons per square meter for the screw. So hopefully you can appreciate that applying the same force to these two objects leads to totally different pressures, because for the screw, the force of 10 newtons is being applied over a greater area because the point of the nail is much less. Okay, and this is something we see in nature quite frequently. So if you think about a polar bear or a snow leopard, instead of having tiny paws like this, like tiny paws like a house cat, they have really broad paws. And they have these broad paws so that they can apply less pressure over snow or ice. So if you think about a polar bear, for example, if they had really, really tiny feet, they would be exerting a lot more pressure on the ice and risk punching through. So that's why many animals who have to walk through a lot of snow or on top of ice have really broad feet so that they can spread out their weight as much as possible. Okay, so we've defined what pressure is, we know the formula, and we've looked at some examples. Something that's very important to notice here is we've used the SI unit for force, which is newtons, and the SI unit for distance to calculate the area, so meters squared. And this unit here, newtons per square meter, is known as the Pascal. So instead of saying 2,000 newtons per meter squared, what we can do is say this equals 2,000 pascals. Okay, so we can say 1 newton per square meter equals 1 pascal, and that is the SI unit for pressure. And just like with the other SI units, if we have 1,000 pascals, we would call it 1 kilopascal, and then use those same prefixes and suffixes for the powers of 10. Okay, so now what we're going to do is we're going to look at pressure again, more from a perspective of gases. So when we think about pressure in terms of gases, we're talking about the particles colliding with the walls of the container, and those collisions are going to lead to a force being exerted on the walls of the container. So that's what it says on page 14 here. Every time a particle collides with the wall, it exerts an outward force which is measured as pressure. The gases exert pressure on any surface they come into contact with because the molecules are constantly in motion. Remember that from the kinetic molecular theory. And what we're going to be doing in this unit is talking about how temperature, volume, and the number of particles affect the pressure that a gas exerts. So again, I like to use diagrams a lot here. So if we think about a propane tank that might be under a grill, for example, we're going to have molecules of propane here that are going to be in random constant motion colliding with the walls of the container, and they're going to be exerting a pressure on it. However, let's just say this is how our gas tank originally looks, right? It has, we're just representing it here, let's just say 5 molecules of propane. So let's just say we use the grill to make some barbecue chicken or something like that. We're going to use propane, so there's going to be less molecules in the tank. So it'll look something like this. Instead of having 5 molecules, it'll have 3. So because there are now less particles in the container, there are going to be less collisions between particles in the walls of the container, so that means less pressure. So hopefully we can understand why the number of particles determines pressure if we're keeping the size of the container constant. Okay. So we also have something called atmospheric pressure. So this is pressure that's exerted by the air in the atmosphere. And the reason why the atmosphere has pressure is because the molecules of air have mass, and they're being attracted by the Earth's gravity. So hopefully you remember that force equals mass times acceleration, right? And the molecules of air are going to have a mass, and they're also going to have acceleration because these molecules of air are going to be acted upon by gravity. So it'll be the same acceleration due to gravity that we would have been talking about in grade 10 science, which, if I'm not mistaken, is 9.8 meters per second squared or something like that. We don't really need to know the exact value now. We just need to understand where atmospheric pressure comes from. So atmospheric pressure is also going to vary with altitude, and that's because the amount of air molecules is going to change the further we move away from the surface of the Earth and towards space. But most of the time we're going to be talking about the atmospheric pressure at sea level. Okay, and we measure that with a barometer. Okay, so now we're just going to quickly talk about some units of pressure before we start doing some really quick calculations, which is the meat and bones of this lesson. So the SI unit of pressure is the Pascal. And remember that the Pascal is newtons per square meter. Okay, it's named after Blaise Pascal, who was a French mathematician and philosopher. We need to remember that 1 Pascal is equal to 1 Newton per square meter. The pressures measured by barometers and manometers can be reported in millimeters of mercury as well. So this is usually what a weather forecaster will say the atmospheric pressure is. They'll say like, oh, the pressure is rising today by however many millimeters of mercury. Okay, and there's also a unit called the torr, which is named after an Italian guy called Torricelli. And 1 torr is equal to 1 millimeter of mercury. Okay. So at sea level, the average air pressure is 760 millimeters per mercury when the temperature is 0 degrees Celsius. And this is most often the unit people are going to use to describe pressure at when we're talking about atmospheric pressure. Okay, so ATM. So the conversion factor that we need to keep in mind for this unit is right here in gray. And we need to remember that 1.0 atmosphere equals 760 millimeters of mercury, which is going to in turn equal 760 torr, which is going to equal 1.1.3 kilopascals. Okay, and we're going to leave these last two blank for a while because we don't need them for the calculations that we're going to be doing. So often in chemistry we talk about standard temperature and pressures, and these are just so that the results that we communicate with colleagues are communicated with results that are reproducible. So we usually abbreviate standard temperature and pressure as STP. Okay, so we define our standard conditions being 0 Celsius and 1 atmosphere pressure. And we say at standard temperature and volume, an ideal gas will occupy 22.4 liters per mole, which is what we did in our stoichiometry unit. Okay, so now we're going to look at page 15, just to do some examples of pressure conversions. These are pretty straightforward, I think. You should be pretty comfortable doing this after we do an example. So for example 1, it says convert 0.85 atmospheres to millimeters of mercury. So that's 0.875 atmospheres to millimeters of mercury. So the first thing we can do is use the formula that we've learned previously, which is multiplying what you have by what you want to gain and dividing it by what you want to lose, and that'll give you what you want. Remember that the units for what you have and what you want to lose are always going to be the same. So what we have currently is 0.875 atmospheres. Okay. What we want to gain are millimeters of mercury. What we want to lose are atmospheres. So what we need to do is plug in our conversion. So we know it's 760 millimeters of mercury to 1 atmosphere. So once we multiply those two, once we do this conversion, right, the atmospheres are going to cancel, leaving only millimeters of mercury. And then our final answer is going to be 665 millimeters of mercury. So again, you multiply what you have by what you want to gain, divide by what you want to lose, and keep in mind what you have and what you want to lose are going to have the same units. You set up your conversion factor that we get from here, plug that into your calculator, and then you get your answer. Okay, so we've done example 1. Now let's quickly look at example 2. I'm just going to quickly grab my calculator. Okay, so it says convert 745.0 millimeters of mercury to atmospheres. So again, we're going to take what we have, which is 745 millimeters of mercury, and we're going to multiply it by what we want to gain, which is atmospheres, and divide by what we want to lose, which is our millimeters of mercury. Okay, then we plug in our conversion factor, which is 1 atmosphere for every 760 millimeters of mercury. Put that in our calculator. So 745 times 1 divided by 760, and that gives us 0.98 atmospheres. That's pretty much what you do for all of these, pretty much, is just use that same have multiplied by what you want to gain and divide by what you lose. Okay, and the last thing I'm going to do in this video is just do one more of these so that we're crystal clear, but I'm just going to use some of the units that we haven't looked at. So I'm going to do question number 3. So we need to convert 52.5 kilopascals into atmospheres. So again, we take what we have, which is the 52.5 kilopascals, multiply by what we want to gain and divide by what we want to lose. So we want to gain atmospheres, we want to lose kilopascals. So now we just plug in the conversion factor. So we know 1 atmosphere equals 101.3 kilopascals. Okay, and then our units of kilopascals cancel. So you just do 52.5 multiplied by 1 divided by 101.3. That gives us 0.52 atmospheres to 2 decimal places, and yep, that matches the answer that we were given on the bottom. So that's pretty much it for this short video. I'm going to keep these sort of under 20 minutes each, and then I'll be making another video shortly.